Okay, so we are here in the second part of this video, which is the okay, not really, let me say complex. Okay, let me just use that word, because where we start from, okay, now to illustrate a more complex model, recall that we in the previous video we talked about, we made mention of something, that this equation 1 can range from simple algebraic expressions to complex differential equation. Can range from simple algebraic equation to complex complex differential equation. So today, in this video, we are going to look at the complex. This here. Okay. Now, there is a reason why we had to name each of the equations, and here comes the importance of that, because we are going to take from equation 3. From equation 3, we are going to express it in the form of a differential equation, and according to what was said in class, which really made like super sense. Okay, let me just read the thing and you hear this stuff. Now, to illustrate a more complex model of this kind, Newton's second law can be used to determine the terminal velocity of a free falling body as it gets close to the surface of the earth. Okay, so let's say we have the surface of the earth. Okay, yeah, then we have a free falling body, and it happens to be a parachutist. Yeah. Okay, now it may not look like really nice, but just use your imagination to make the drawing better. So now the parachutist falling down, okay, or doing what he's doing. Now, the terminal velocity, that is the velocity at what is the velocity when it gets close to the surface of the earth? So we are looking for the terminal velocity in this case. Now this is the earth in this case now. Yeah, so in this case, that's the earth. Okay, so this is the earth in this case now, and that's our free falling body. Now, as the body gets close to the earth, we can determine the terminal velocity. What will be the velocity when it gets close to the earth? I've said that over and over again. So with that in mind, what should we do? And we said our free falling body now is the parachutist. Okay, a parachutist and a Jewish Superman are big. So now, so what we'll do, we are going to express the acceleration as time rate of change of velocity, and then substitute into equation 3. So we get equation 4 from that. Now, this is our equation 3. So expressing acceleration as time rate of change is just like this, which we know as acceleration is change in velocity with time. That's it. Okay, so I'm not going to name this equation 4. I'm not going to name this because it wasn't named in class. I'm just trying to, but you can name if you want to. It doesn't really mean, but this is a well-known fact already, that acceleration is change in velocity with time. So dv dt is acceleration. So this dv dt substitute into equation 3. Therefore, equation 3 will now become, becomes dv dt equals what? F over m. This is equation 4. Okay, beautiful. So we are following so far now. Okay, right now. Okay, so at this point, dv dt equals f divided by m. Now f is not just force, it is net force. Net force, that means it is the sum of all the forces acting on the body, or acting on the parachutist in this case, on this guy. So now the force is acting on this guy, on the parachutist, basically two: downward force and upward force. Now for our downward force is from the pull of gravity, okay, and which is the acceleration due to gravity multiplied by his mass, because force is acceleration times mass, or mass times acceleration. So the force is acting on this guy. We have two forces. So the downward force acting on this guy, or the parachutist, let's denote that by Fd. Fd is the force of gravity, which is mass times acceleration due to gravity. So call this equation 5. Equation 5. Then the upward force Fu, this is as a result of air resistance. Okay, upward force is in the opposite direction of the force of gravity, so we have a negative sign. And then a proportionality constant, and this is velocity, of course. So the proportionality constant is known as drag coefficient. Okay, known as drag coefficient, and the units, its unit is kilogram per second. That's its unit. So call this equation 6. Okay, so these are the forces acting on the body. So force, the net force, is the sum of, is made up of sum of downward force, and then upward force. So we can write that as F. Let me put that here. We can write that as F equals Fd plus Fu. Call this equation 7.7. Equation 7. Okay. Now, please pardon how this thing looks like. Okay. So we've gotten this now. We can take this and substitute back into equation 4. Since we've gotten what this is, now we can say dv dt from equation 4, right? Equation 4. dv dt equals, look at equation 4, F over m. But in this case, our F now is the sum of F and then U. Let me not jump, okay? So let me just write the whole thing. I don't want to jump. So F, and F we said what is Fd. Let me write it out here. Fd plus Fu all over m. This is the m we already have. I think I should just expand this thing. Okay, better. So, and I am not going to name this equation 8 because it wasn't. I'm just trying to, make it clear while I stick to what was given in class. So now I believe we are together. So FD plus FU cleared. Now FD is GM, FU is minus CV. That means we can have this, we can have this as dv dt equals FD is GM, right? Then CV is negative. Let's leave this here. Negative CV all over this. Okay? Now, of course, this minus and plus sign, we'll have a minus sign there. So should I just cancel that out? Let me just even wipe that out now. Save space. Okay, and wipe this out. Yeah, better. Now this is equation 8. Am I right? Yeah, 8. Equation 8. Beautiful. Now this is also, we can simplify further to have dv, let me zoom in. We can simplify further to have dv over dt equals, look at this, gm minus this. Like if we separate this thing, like take this gm divided by m, cv divided by m, this m will this m this m will cancel out this m, so we just have g minus cv over m. So this will result to g minus c over m, where we have v here, equation 9. Beautiful. Good. Are we together? Now, with that being said, equation 9, recall that we are looking for the terminal velocity. Okay, so taking the at initial condition, that's at initial conditions where velocity is 0 and time is 0. Let's leave that out for now, but note that we're going to use that later. Okay, so from this, looking at this is already a differential equation. Okay, because we already of the order 1, differential equation of order 1. So yeah, so this differential equation, and it's of the first order, because the highest power we have here is 1, invisible 1. So let's if we differentiate this, okay, we'll arrive at an answer. Okay, but let me just say the whole thing here. To differentiate this, you use the form, let me just, dv over dt plus c over mv equals g. This is not equation 10, okay? Equation 10 is what we'll end at. Let me even name this equation I. Okay? Or equation I, let me leave it at that. Now, from this equation, or equation A, or I leave it like that. So, from this, looking at this, guys, you can solve this differential equation using the method of integrating factor. So if you do that on this, you arrive at this. V, shall I use another color on this? You arrive at V of t. V of t equals GM over C then 1 minus exponential minus c over m. Yeah, that's correct. Okay, so you will arrive at this as final answer, equation 10. This expression gives us the terminal velocity. At time 0, we'll have a value. At time 0, we'll have a value for velocity. At time 2, at time 3, 4, and so on. Okay, so yeah, okay, as a recap of the recap, we looked at taking from the simple model, simple algebraic mathematical model, we got to a complex model. We got to a complex model by taking acceleration. That's considering acceleration as the time rate of change of velocity, which is the same thing as saying a equals dv dt, and then we substitute into equation 3 to give us equation 4, and then considering the net force, which is downward force and upward force, substituting back into equation 4 to give us equation 8, okay, of which simplifies to give us equation 9, and then once you just change your subject formula, that's g should be on its own, and once you do that, you arrive at a differential equation in which you can get the terminal velocity by using the method of integrating factor. Yeah, with the boundary conditions of v equals 0 and t equals 0, you arrive at this as the answer. Okay, so thanks for watching, and see you in the next video. Bye for now.